Hi, everybody. Okay, so now that you have seen the spectral theorem and how to actually find an orthogonal decomposition, it's really this just diagonalization of a symmetric matrix with the extra little catch that when you have an eigenspace that has at least more than one vector in its eigenbasis, you have to find an orthogonal basis for that eigenspace. That means that you need to use the Gram-Schmidt process for that particular eigenspace. Beyond that, it's just the same things before. It's not really new. It's just this neat extra result that we get. Thing is, though, there's this nice connection between projections and orthogonal diagonalization. And it's certainly something you should see. It's not something we use very often. Like, you really won't, but it is a nice way to view the process. So if you say that a matrix is orthogonal and diagonalizable, that means that there's a matrix Q of a bunch of eigenvectors that are actually orthogonal to each other. So if you take Q transpose times A times Q, you get a diagonal matrix whose entries on the main diagonal are the eigenvalues. Notice if you take that matrix, that diagonal matrix, you can think of it in column form. It'd be the first eigenvalue times the standard vector E1. The second column would be the second eigenvalue times the second standard vector, E2, and so on. That's useful because you can take this equation and on both sides on the left, multiply by Q, and on both sides on the right, multiply by Q's transpose. Remember now, Q transpose is actually the inverse of Q. So all these products would cancel on the left, giving you just in the end A. And on the right-hand side, you'd have Q times this diagonal matrix, just represented a slightly different way, times Q transpose. But we know that matrix multiplication is associative, so I can choose to do the multiplication in any order I wish. I would choose to multiply Q times this matrix of columns. I can do that because of the matrix column form. Remember that form? I just multiply the Q, the matrix, to each of those columns, giving me that product. But I know what Q times E1 is. It's just the first column of Q. I know what Q times E2 is. It's just the second column of Q. I also know what Q transpose is because I know what Q is. So then the rows of Q transpose correspond to the columns of Q. So I'll just write that down. This is what you get then when you write it that way. Notice then A is expressed as a product of two matrices, but the first matrix is written in column form. The second matrix is written in row form. This is set up exactly for block multiplication. I mentioned we do this at least once or twice. So then this is block multiplication. This is called the outer product for a matrix. It's also called the column row multiplication. If you do so, you get this. So then A is a sum of matrices. That's what that says. A is a particular sum of matrices. Each matrix in that sum is a matrix formed by taking a vector in the column, a particular column of Q, written as a column matrix, taking its transpose and multiplying the column form to the row form to get a square matrix, and then multiplying it by an eigenvalue. Now, I know you look at it and go, that seems, why would we want to do that? Like, that seems, the other stuff is easy, Professor Dugan. I understand that. It's just a matter of me just cranking things out. Why do we care? So the reason is because you need to make more connections. The more connections you make in more linear algebra, the better your chance to encounter a new problem and see how to attack it different ways. So I'm trying to build up your geometric understanding of things. Okay, so then, well, what is, if you have a unit vector U, what does U times U transpose mean if U is written as a column? I told you already. If you remember, if it's a unit vector, the projection of the vector X upon U is actually can be done by matrix multiplication. Just multiply X on the right to the matrix of U times U transpose. So if U is a unit vector, U times U transpose is a projection matrix. It's literally the standard matrix for the transformation to project a vector upon the line spanned by U. Seen that way, this is actually a sum of projection matrices. So that's it. The spectral theorem is actually another way to look at projection, except twisting it a little bit, because projection, we shouldn't have these scalars. You shouldn't have lambda 1 in front of the projection matrix for Q1. It should just be 1. If it really is projection, it would have only a 1 there, but it doesn't. So then this expresses then the matrix A as a sum of multiples of projection matrices, where each one is projecting upon a different eigenvector, each one in the eigenbasis that corresponds to the eigenbasis for A. It's neat, right? All right, so then you should see that used once. This is actually useful in order to find, if you want to find a certain matrix that has a certain number of eigenvectors and has a certain number of eigenvalues, it's useful to use. As an example, I want to know, can you give me a 2x2 matrix that has 3 and -3 as eigenvalues, and it actually has these orthogonal eigenvectors? Well, yeah, because the minute you told me that you have 2 orthogonal eigenvectors, instantly the matrix A had got to be, it has to be orthogonal and diagonalizable, which means then it has to be symmetric. So I know what it looks like already. It's got to be a symmetric matrix when I'm done. But I can do more. Notice that if you form the matrix Q, oops, sorry. If you form the matrix Q1, and that will be 1, 2, and I'll orthogonal, I'll normalize it. So I'll divide this by its length. So its length here is square root of 5. So I'll divide by 1 over square root of 5. That vector now is unit length. And then form the vector Q2, which would be the vector -2, 1. And I'll again normalize it to make sure this vector is unit length. That would then be, once again, 1 over square root of 5. I can now tell you what the matrix A has got to be. The matrix A would have to be the first eigenvalue. Let's say the eigenvalue is 3, and it goes with the eigenvector Q1. And then I just multiply it by Q1 transpose. Then I add on to it the next eigenvalue, and then it's corresponding to the other eigenvector. Let's say then that would be Q1 times, Q2 times Q2 transpose. So I'm just going to write that out. That's then 3 times. Now, Q1 has a scalar, 1 over the square root of 5. In this matrix multiplication, I'll just put those scalars right out front, because I can put them anywhere I want. Then I'll have what's left over, 1, 2 times 1, 2, column and then row. Then I'll subtract 3. And then again, the Q2 has a scalar, 1 over the square root of 5. I'll just take that out. Get 1 over the square root of 5 times 1 over the square root of 5. And then you have Q2 in column form, which is -2, 1. And then in row form, -2, 1. That's it. All I have to do is just multiply that out. So that would then equal, it's clearly just 3/5. When you multiply this column vector to this row column, it becomes a square matrix. And it's 1, 2, 2, 4. And then from there, I would then subtract 3 over 5. And then this would then be 4, -2, -2. And then this would then be just 1. And if you add that up, that's the matrix. Or at least that's one of them. That's one matrix where this is true. This is one matrix that has this particular has these eigenvalues and has these eigenvectors. So there's more though. There's other answers too. But then this is it. So I believe that's enough for this particular video.